So hello, we're the team. We're team. We are not ready for this. I'm Matija Lagator.
I'm Tionney next.
And I'm Daniel Washburn.
We're gonna present our term project today. It's a term project on particle collisions, and first off, we're gonna start talking about time-driven collisions, in which every half a second we moved the balls a certain distance. It was a randomly generated velocity. The ball started off with a randomly generated velocity and speed, and every half a second we check if they collide with the walls. In this part of the project, we still haven't incorporated the ball-to-ball collisions, so it roughly looks like this. So you see the balls are passing through each other, but they're bouncing off walls, and this was good for this event. So as long as balls are not hitting each other, because for a larger number of balls and ball-ball collisions, this would take a long time, and that's why we developed the
Priority queue.
the priority queue and the event-driven simulation instead of the time-driven simulation.
Did you start again? Okay, so the key to event-driven simulation is the use of a priority queue. We base our priority queue off of a min heap, in which events that are going to happen the quickest are at the top of the priority queue and are popped off first. And as events are popped off of the priority queue, they happen on the real screen. So in our priority queue, we have an insert, which inserts an event into the priority queue and sorts it based on the time it's going to happen. And we have a pop min, which pops off the event that's going to happen the closest time and makes it happen on the screen.
So, this priority queue, like you said, is used to order all of the events. So the way the event-driven simulation works is, first, once you have all the balls created, you predict all of the possible collisions they could have with each other or the walls based on which ways they're going at that point, and you put all of those events onto the priority queue. Then it's fine. You can just cut out stuff.
Final right there.
Is it? Yeah. So we predict all of the possible collisions that the balls could have with each other or with the walls, and then as we go through time, we keep moving the balls in their normal trajectories until we get to the first event that we know is going to happen. And then when we get to that event, we check to see if it's still valid, and it'll be still valid if nothing else has happened in between to one of the balls involved. So then if it's valid, we make the balls bounce off of each other or the wall in the way that they're supposed to according to physics, and then predict all of the new possible collisions and keep going. So now we'll demonstrate this.
So here we're gonna run the final version of our code for generating 5 balls, and it looks something like this. You see the balls have random radii and random colors, random velocities and starting positions, and they bounce off each other, and each collision pops off the event from the priority queue. And also I'm gonna run it on 20 balls, which I think looks much cooler, especially with all the colors. And yeah, that's pretty much how particle collision looks.
Okay, so after we finished up with the ball simulation, we thought it would be really cool to make a sort of a game out of it. So we made it so there's one special ball that you can control using keys on your keyboard, and you move around. It's red. And basically, if you hit another ball that's the same size as you or smaller, then you sort of eat it and your ball gets bigger and the other one disappears. But if you run into a ball that's bigger than you, then you die and you lose. And once you eat all the other balls, you win. So it's kind of hard when there's a whole lot of other balls. I don't know what else to say.
Fear the little red ball.